In this example, we're told we have two ME309 students who want to measure the height of the mechanical engineering building, shown down here. This is actually an old picture of the mechanical engineering building because we have an addition now that's over on this side. And that obviously wasn't there when this photo was taken. So anyway, there are two different ways to measure the height of the building. So student one climbs to the roof, which is not allowed, don't do that. And then even worse, they drop a ball off or a ball bearing off the top and measure the time it takes for that ball bearing to go from the roof down to the ground. And then knowing from the ballistic equation how the distance traveled is related to the time, they can back out what the time is, or what the height of the building is. And then there was another group of students who decide to measure the height of the building using a protractor. So they go off to the side, measure some distance away from the building, use a protractor to get the angle to a line of sight to the roof line, and then can calculate the height from that. And we're told some of the numbers that correspond to these things as well as the uncertainty. So we're asked to find what's the height of the ME building, which measurement method is most accurate, and is there a particular angle for which the uncertainty in the angle method is minimized. So we're going to try all three of these things. Let's first start with the ball bearing option here, where we drop the ball bearing and look at the height, or calculate the height from that. So if you recall from the ballistic equation, we have something that looks like this, right? Just write this out. This you've covered in a physics class prior to this class. So in this particular case, y naught will be our h. That's the initial starting height. The y dot naught, this is the initial velocity. That's going to be 0 because we're just going to drop it. We're not going to throw it. And then y would be 0 because that's where the ground is. So you can rearrange that equation to solve for the height. That'll just be 1/2 g. I'll just write it as capital T squared. So capital T is the height you measure, and h is the height of the building. So I'm sorry, capital T is the time you measure, and h is the height of the building. So in this particular case, we're told that capital T is 2.2 seconds. That's given right up here. And we, of course, know that g is 9.81 meters per second squared, so we can solve then for the height, and it comes out to be 23.7 meters. Now we have to factor in the uncertainty. So the relative uncertainty in the height of the building, which of course is just the absolute uncertainty in the height divided by the actual height. So the h there is the 23.7 meters. That's going to be the square root of the relative uncertainty in the height due to the uncertainty in g squared, plus the relative uncertainty in the height due to the uncertainty in t squared. Well, first of all, the first term, the relative uncertainty in the height due to the uncertainty in g, we're going to say is very, very small, so we can neglect. So it's very, very small, we'll neglect it. And the reason for that is because we typically know the acceleration due to gravity accurately, so we're going to say that that's small, that the uncertainty in the time measurement just far outweighs the uncertainty in the gravitational acceleration. Okay, so now we need to calculate the relative uncertainty in h due to t, and that's just going to be 1/h times dh dt times the absolute uncertainty in the time t. So we can substitute in for h using our equation from right up here. Substitute that in, so that'll be 1/2 gt squared. Then we have dh dt, which will be g times t, so that's just taking the derivative of this equation with respect to t, so that'll just be g times t, and then we have the absolute uncertainty in the time measurement. And if you look at that, there's some things that cross out. We have the g that crosses out, there's one of the times that crosses out, and we'll get 2 times dt over t, which is just 2 times the relative uncertainty in the time. Thus, you see the relative uncertainty in the height will be 2 times the relative uncertainty in the time. And I get that by taking this expression, which was the UH comma T, and I just substituted it in right up here. And then since we neglect this one, this is just squared and square rooted. So that's how we end up with that expression. So to find the relative uncertainty in the time, we take the absolute uncertainty in the time, right here, divided by the actual time. So if you look in the problem statement, the absolute uncertainty in the time measurement is 0.2 seconds. The actual time is 2.2 seconds. So we can write this out. Oops, let me try to fix that. So the relative uncertainty in the time is the 0.2 seconds divided by 2.2 seconds. So that value comes out to be 0.091, which means that the relative uncertainty in the height comes out to be 0.182, so about 18%. And thus, the height measurement using this approach will be 23.7 plus or minus, and then if we multiply that 23.7 times the 0.182, that comes out to be 4.3 meters. So that's the height measurement using the ball dropping method or ball bearing dropping method. All right, now let's go to the other method where we use the angle. So if we look at this picture here, you'll see just from the geometry, tangent of theta is h over L. So L, or I'm sorry, let me rewrite that. So h is L tangent of theta. All right, so let me just recopy that here. H is equal to L tangent theta. So we have our measurements here. So we're told in the problem statement that L is 20 meters and theta is 44.4 degrees. So L is 20 meters, theta is 44.4 degrees. So if you plug in the numbers for that, you'll get H comes out to be 19.6 meters. So a little different than what we found up here. Here it's 23.7, here it's 19.6, but you got to remember there's a decent amount of uncertainty in the ball dropping method, and then the uncertainty for the angle measurement we haven't figured out yet. That's our next step. So to find the relative uncertainty in the height measurement using this approach, it'll be the relative uncertainty in the height due to the uncertainty in the length measurement squared plus the relative uncertainty in the height due to the uncertainty in the angle measurement squared. And to find what each of those terms are, let me go down here. We'll have to use the derivative method here. So relative uncertainty in height due to the uncertainty in L will be 1 over h times dh dl times the absolute uncertainty in the L measurement. So we'll just substitute in for this. So h is L tangent theta. dh dl will just be tangent of theta. And then there's our absolute uncertainty in L. And you see the tangent thetas cancel out, and we're left with dl over L, which is just the relative uncertainty in L. So that's that term. Now let's do the relative uncertainty in h due to the uncertainty in theta expression. So that'll be 1 over h dh d theta times the absolute uncertainty in theta. Okay, we'll substitute in for h, that's L tangent theta. When we do dh d theta, let's take the derivative of a tangent theta. That's a secant squared theta. So this comes out to be L secant squared theta. Secant is just 1 over cosine. Okay, so that's that derivative, and then we have the absolute uncertainty in theta. So when we look at this, you'll see the L's cancel out. And then if I expand out, like I said, secant squared is like 1 over cosine squared theta. And tangent, of course, is sine theta over cosine theta. So we can divide out one of the cosines, and what we'll be left with then, I'll have to mark this down here, what we'll get in the end here will be a little more space. Try that one more time. Okay, so what we're left with down here then is 1 over sine theta cosine theta, and then that will be multiplied by delta theta. And to put it in terms of the relative uncertainty in theta, what I'm going to do is I'm just going to divide by theta and multiply by theta. That just makes it a little more convenient. So we have theta over, and the other thing I can do, by the way, is use a trigonometric identity for this sine theta cosine theta. That's the same thing as writing 1/2 sine of 2 theta. So what I've done here is I've used a trigonometric identity to write that as 1/2 sine of 2 theta, and then I multiplied it and divided by theta so that I can write this as the relative uncertainty in theta. So this now is our expression for the relative uncertainty in h due to the uncertainty in theta. Now when we combine these together, the relative uncertainty in h, the total relative uncertainty there, will be this term squared plus this term squared. So it'll be theta over 1/2 sine of 2 theta squared times u sub theta squared plus ul squared. So that is now our relative uncertainty in the height measurement. Well, we can now plug in the numbers that we're given. So we're told that theta was 44.4 degrees. We're told delta theta was, go back up to the problem statement. So the absolute uncertainty in the angle measurement was plus or minus 1 degree. While we're here, the absolute uncertainty in the length measurement was 0.5. So I have to remember both of those. So 1 degree, L was 20 meters, and delta L was 0.5 meters. So we can calculate the relative uncertainty in the theta. Of course, that's just d theta over theta. And when we plug those numbers in, we'll get 0.022. And then the relative uncertainty in the length measurement comes out to be 0.025. So when you plug everything in, the relative uncertainty in the height measurement comes out to be just over 4%, 0.043. So then our height measurement using the angle approach, let's go back up here for a moment, will be the 19.6 meters plus or minus, and then if I take 19.6 times 0.043, remember that UH is just the absolute uncertainty in H divided by H. So to find the absolute uncertainty in H, we'll just take UH, which here is 0.043 times H, which is 19.6. And when we plug those numbers in, this comes out to be 0.8 meters. So you can see that our uncertainty in the angle measurement is much smaller than the uncertainty in the ball dropping method here. So we would be much better off using the angle measurement to get a more accurate reading for the building height. Not to mention, it's a whole lot safer. You don't have to climb to the roof and you don't have to drop stuff and worry about clobbering somebody on the ground. But anyway, from an engineering perspective in terms of accuracy, we would be better off using the angle method. Okay, the very last part of the problem, let me go back and look at it. It says, is there a particular angle for which the uncertainty in the angle method is minimized? So can we do even better? Is there some particular angle? Here we're using 44.4 degrees, but maybe there's an angle that we could use on our protractor to make the measurement even more accurate. So the way you do these kinds of optimization problems, it usually involves the typical calculus approach where you take the derivative of the function with respect to what it is you're trying to optimize. So what we're trying to optimize is the angle, and the function we're trying to minimize is u sub h. So what I want to do is really I want to find an extremum point. I want to find what when duh to theta goes to 0. That'll give me either a maximum or a minimum or maybe some inflection point. So we want to set that to 0. And actually it's a little easier for us to, when taking the derivative, is to take the derivative of UH squared over d theta. Just because we have the square root in the expression right here, it's a little easier if we just square it so we don't have to worry about the square root. It won't affect what the critical angle is. It just makes our derivative calculations easier. So we'll set that equal to 0. And if I just write that out, we have d theta of that's theta over 1/2 sine of 2 theta, that whole quantity squared, times u sub theta squared plus ul squared. So I'm trying to take the derivative of that with respect to theta, set it equal to 0. Well, first of all, you can see d theta of u sub L, that just goes to 0. So we don't even have to worry about the u sub L part. It doesn't factor into it, because this is not a function of theta. U sub theta is a function of theta, so I should really expand that out, right? So this will be, let me write that out. This will be theta over, I'm going to put the 2 in the numerator there just to make it a little easier. So this whole thing squared, and then the u theta squared, that's really d theta over theta, that quantity squared. And I'm not going to worry about the u sub L. We already said that d theta of that goes to 0, so I'm not going to worry about that. But now you can see that we can cancel out the theta squared there and the theta squared there. And I can also bring this 2 outside the square brackets because it doesn't factor into that. And then when you can divide through by it, right? So you'll get a 2 that comes outside, and then since it's equal to 0, I can divide by 2 and it's just fine. So I'm going to do that as well. So now I have d theta squared all over sine of 2 theta squared. So that's where we are now. All right, so let's do the next thing. The delta theta, that's the absolute uncertainty in theta. That's a constant, right? So that's not really a function. That doesn't vary as we vary theta. This is just plus or minus 1 degree. So we can pull that outside the square brackets or outside the derivative as well, and then divide through by that. So we don't have to worry about that one either. So what we finally have, and by the way, I can change the partial derivative to an ordinary derivative since this thing is only a function of theta. So this is now derivative of sine of 2 theta raised to the minus 2 power, right? Because it's in the denominator, that's where the minus comes from. It's squared, so that's where the 2 comes from. Now I want to set that equal to 0, so when I take that derivative, I need to use the chain rule. That comes out to be minus 2 sine of minus 3 2 theta. There's a cosine of 2 theta times a 2. I think I did my calculus correct there. This is the chain rule for taking that derivative. So that's what that expression is. Well, the 2 and the minus and this 2, those can all be divided out. So what I'm left with is what I'm left with then is cosine of 2 theta all over sine of 2 theta, the whole thing cubed, equal to 0. All right, so under what conditions is that equal to 0? So first of all, it'll be 0 when the cosine term goes to 0. So that will occur when theta is equal to 0. Or I'm sorry, no, that'll occur when theta is 45 degrees. Sorry about that. So when theta is 45 degrees, that term will go to 0, because then you'll get cosine of 90 degrees, which is 0. So that's why that goes to 0. And then in the denominator, that'll go to 0 when this, well, if you look at this, this won't make it go to 0, right? There's no way to make this go to infinity. So it only occurs when theta is equal to 45 degrees. Okay, so that's the angle at which we'll minimize our uncertainty in the calculation, right? And so again, just to kind of remind you what we did, since there was a lot of math involved, is we were trying to find a point at which we can minimize the error in the relative uncertainty of the height measurement by changing the angle. We want to find an angle that minimizes that uncertainty. So we'll use our old calculus approach of taking the derivative of u sub h with respect to theta, set it equal to 0. I did just u sub h squared because it's a little easier to do the derivative and it doesn't affect our result. Then all of this is just the math involved of taking that derivative, setting it equal to 0. We get down to this point, and we see that the only way for this to equal 0, it would be, and the only angle that makes sense would be when theta is 45 degrees, because cosine of 2 times 45 degrees is cosine of 90 degrees, which is 0. And of course, we only want acute angles in this case. The denominator, there's nothing in the denominator. One of the things you'll see is, well, yeah, you can't make this equal to 0 by fiddling with the denominator. It's only in the numerator here. So to optimize or minimize the uncertainty in the measurement, we want theta to be 45 degrees. And if you go back and look at the problem statement, we said that the angle is 44.4 degrees. So we're almost really at the best angle that we should be using to get the most accurate measurement. If we were at some other angle, the uncertainties would actually be bigger. And you can sort of see that if you come over here. You can see how it might be modified as we changed, if we change the angles and such. By the way, one of the things I should point out, I guess I didn't state this carefully here, but I should have made note of this, is when we're doing this calculation, you should use radians rather than degrees in evaluating this theta. That's important. So I should just make a note here, convert to radians. Generally, you're in any sort of calculation involving angles and such, you're just better off using radians rather than degrees. You're less likely to make mistakes that way. So I just want to point that out. When you're plugging in numbers into this highlighted bit there, you should be definitely using radians. And I actually did that when I calculated this uncertainty down here.